Okay, so now we've got to partial differentiation. We are given a function y equals 6 plus 3x plus 16z plus 4x squared plus 2z squared. And our task is to differentiate it twice, one with respect to x and once with respect to z. And so this is where we differentiate with respect to one variable, holding the other constant. So let's start. You remember we use the curly D. The curly D, instead of the normal D, signifies that we are differentiating with respect to x and holding some other variable constant. So here we go. So now we are just differentiating with respect to x. So we've got 6 goes away, doesn't it? Any constant goes away when we're differentiating. Differentiate 3x with respect to x, it becomes just 3. There's no power to multiply thereby. Now 16z is just a constant in this process, so it goes away. Now we have to differentiate this, multiply multiply the number in front of the x by the power, gives us 8, drop the power by 1, x to the power of 1, which we don't show, just x. And 2z squared is a constant, so we ignore it. So now we're going to repeat, but we're going to this time differentiate with respect to z and treat x as a constant. So here we go. 6 goes away, 3x goes away, it's just a constant. 16z becomes 16. 4x squared goes away, no z there. 2z squared becomes, multiplied by the power, 2 times 2 is 4, drop the power by 1, so we don't show a power. So that's our first bit. Now we have another function, plus 2x squared minus 4z plus 6x. Hopefully I've written that down right. So now we're going to differentiate again with respect to x. Here we go. 4z squared is a constant. Differentiate as normal here. 2 times 2 is 4. Drop the power by 1. Constant plus 6. So we're bombing through now, aren't we? So now we're going to differentiate with respect to z. Here we go. 2 times 5 is 10z. Drop the power by 1. 2x squared goes away. Minus 4z becomes minus 4. 6x goes away. All right. B. Given the production function, so y there standing for output, k is for capital, that's a third, L to 2/3. We know this is a constant returns to scale because these two powers add to 1. So find the value of y when k equals 27. So what we're saying is k is 27, so we're going to substitute that in. And L, labor, is 64. 2/3. I haven't said without using a calculator. I do sometimes. Let's use this as a way of practicing. We could just put this into our calculator. Let's just use this as a way of practicing our understanding of powers. A third is simply the cube root. And what's the cube root of 27? Well, it's 3, because 3 times 3 times 3 is 27. Now here, we've got the cube root squared. So we could write this as we wanted, like that, and do it in 2 separate processes. So we've got y equals 3 times 3 times. Now the cube root of 64 is 4, because 4 times 4 times 4 equals 64. So we've got 4 squared, and now we can finish 3 times 3 times 16, which equals 3 times 3 times 16 equals 144. But we could have just slapped it into a calculator here. And we could have had 3 times 27 to the power of 1 divided by 3 times 64 to the power of 2 divided by 3. Can you see that? These are division signs. 144. Good. C. Using the above production function, so that again is this function, find dy by dl and find dy by dk. So here we are, we're having to partially differentiate a production function which is a function of 2 variables. So I should have made these curvy ones because we're going to differentiate one with respect to one and hold the other constant. So here we are treating k as just a constant. We are only differentiating with respect to L. Yep. So this is just constant. So we can write 3k 1/3. We multiply by the power. So I'm going to bring that here. Yeah, we could put it there. It doesn't matter where we put that power. And drop the power by 1. See, we're doing what we always do. Here's our constant. Multiply by the power. Drop the power by 1. Well, what is 2/3 minus 1? Well, that takes us into negative 1/3. You can do that on your calculator if you need to, if you don't have that feel for fractions. I can show that. So here's me using the fraction button. 2/3 minus 1. Can you see that? Gives us minus 1/3. So we can cheat, do it on our calculator. So we drop the power by 1. So let's just tidy this up. Look, 3 cancels out. So we've got 2k to 1/3, L to minus 1/3. So that's a bit hard to interpret that, isn't it? So, so we're going to do our thing where we can tidy this up a bit. That's 1/3, sorry. 1/3. Now we know that L to the power of minus 1/3 is the same as putting it to the bottom and having the power positive. A negative power always implies that it's in the wrong place. It should go to the bottom. Or if it's already at the bottom, it needs to go to the top. So we can take this term, put it at the bottom, and now it has a positive power. And we can do one more thing, because if both k and l are raised to the power of 1/3, we can sort of put brackets around and have a general power of 1/3, which gives us an easier way of interpreting this. So we can see that y changes, that the rate of change of y, so let's say rate of change of y, remember the differential always tells us about the rate of change. The dy by dl tells us the rate at which this thing is changing as this increases by 1 unit. So the rate of change of y, that's what the differential speaks to us about. The rate of change of y with respect to L, with respect to L, is a function of the capital, spelling with the K there, with the capital labor ratio. So we can affect the rate at which output changes as we increase labor by changing or improving the capital labor ratio. And that makes sense, doesn't it? Output per worker will increase if we make each person more productive by investing in technology or whatever to make each person more productive. And then we can do exactly the same on the other side. I can find room. So we're now going to differentiate this, but with respect to k this time, which means this is held constant. So here's me changing the order a bit, but this bit is constant. We don't change that. And we've got k to a third. So I've just I left the 3 at the front, but I brought the L round because that's going to be constant. So k to the power of a third. So we now have to differentiate. I shouldn't have written that yet because we're now going to differentiate this. So we're going to multiply by that power. Got my things mixed up now. We are differentiating with respect to k, and k had a power. So I know what's right. So we're now going to differentiate by multiplying that and dropping the power by 1. So if it was a third and we subtract 1 from it, we get minus 2/3. So that becomes minus 2/3. So I messed that up a little bit. So we hold 3 constant, we hold L constant, and we only differentiate with respect to k. So that means we're multiplying by a third, and we're dropping the power by 1 to minus 2/3. So we can tidy this up a little bit, and that's going to equal L to the 2/3 times k to the minus 2/3, which is the same as L over k 2/3. So here, rate of change of y with respect to k is a function of labor to capital ratio. But we actually have a name for these things, don't we? So the rate of change of y with respect to labor is the marginal product of labor. So we could say the marginal product of labor is a function of capital to labor ratio. And what's this one called? That's called the I'm forgetting, marginal rate of marginal product of capital, except we don't say that, do we? We have a different, I'll come back to that in the next question, marginal product of capital. I'm just forgetting that at the moment, but we don't need it for this answer. We just need to show that we understand that this is the rate at which output is changing as capital changes, and it is a function of our labours to capital ratio. Okay, actually just referring to that, it is just the marginal product of capital. That does seem to be the way it's referred to. Right, okay, so now, oh, I just wrote that off the screen, sorry. It is marginal product of capital. It is normally written like that. But your economics professors might be using different terms as well, but multiple terms for the same thing. Right, so now we're going back to the same production function, but now we're supposed to show that y over L is equal to something particular. So what's this about? So we've got an expression for output. Now we want to make it into an output per worker, or average product of labor. What do we want to call it? Average product of labor? Average output per worker, whatever it is. But if we take the overall amount and divide by L, we are finding the average per worker. So we can't do that to one side without doing it to the other side. So we're dividing both sides by L. Now, it doesn't matter where I write that L, because the top row is all multiplied together and it's divided by the bottom. So it doesn't matter if I divide it into just one of the terms, because it has the same effect. So those two are exactly the same, but it's more convenient for us to put it over the L. Now, L has a sort of hidden power of 1. Every number has a hidden power of 1, unless it has another power, of course. So you will remember when we covered powers that this is going to be 2/3 minus 1. If we're dividing numbers, we subtract their powers as long as the base numbers are the same. So this is 3 to the k over third. What is 2/3 minus 1? Well, it's minus 1/3. We can cheat and do that on a calculator if we need to. There it is. And as we've already done before, this has a negative power, so we can bring it to the bottom and give it a positive power. Furthermore, because these have the same power, we can bracket them and put the power outside. And hopefully that was what we were asked to do. We were supposed to, oh, I think this was the year we might have had an error. Right, back again. Yes, yes, there was an error in some of the versions of the exam, which have now been corrected, but unfortunately the panel to the left is the old one. So I will correct that when I put it up. This is what we were supposed to show, not what it says there. Apologies for that. I will remember to change that. Right, E. Sketch this function. So sketch this function. You'll remember we practiced this in lectures. The thing on this is this side is always going to be the independent variable, so it's always going to be on the vertical axis. And this, now here, this is like our x term. This is the variable k over L. And this is like our y variable, so that's on the vertical axis. So whenever we have a function of anything, any variable, to the power of something less than 1, we know that it's the diminishing returns shape. They just all like that. This makes it a bit steeper, but as we're not putting any numbers on our axes, you can't even see if it's steep or not. So it is simply that. And the reason is as this number gets bigger, this continues to increase, but at a decreasing rate. So I mustn't show it coming down, it's more like that. So we can just easily sketch that. So classic diminishing returns. Provides an economic interpretation of this function. So F, you can write anything sensible, anything you remember from your economics course is fine. So this is showing us that as capital labor ratio increases, that's this, ratio increases, oops, then average output per worker increases, but at a decreasing rate. That will do, something like that. Yeah, remember this is average output per worker. And we're saying that if we give each worker more capital investment, we'll get more productivity out of them, but we can't keep that rate going forever. If we get to a diminishing returns, there's no point at some level of investing anymore. All right.